So, as I said, we need to start the subject with this topic, Boolean algebra. If you look to the difference between the Boolean algebra and the conventional algebra, what you learned in the schooling, the difference will be looking based on the number system. The conventional algebra is based on the number system which is having the radix, the base as 10, whereas the Boolean algebra is having the radix, the base is 2. So that the conventional algebra is based on the decimal number system, whereas the Boolean algebra is based on the binary number system. As we know, in this conventional algebra, we are dealing with the equations and expressions. In these equations and expressions, we are basically relating the variables by using few operators. As similar to the conventional algebra, even in this Boolean algebra also, we are dealing with the equations and expressions. In these equations and expressions, we are relating here also the variables by using few operators. Here also the variables of course, because of the binary number system, we are naming as the binary variables or Boolean variables. These binary variables are Boolean variables. Here also we are representing as similar to the conventional algebra, maybe using this uppercase letters or maybe using this lowercase letters. And to relate these variables, we are having the operators as OR operator, AND operator, and NOT operator. Out of these three basic operators, the first two operators are binary operators, whereas this NOT is unary operator. If you see the difference between the binary operator and unary operator, the binary operator will associate always with a minimum 2 operands, whereas unary operator is associate with only 1 operand. So that we need to start the subject with these operators. This OR operator, symbolically we are representing using any one of this symbol. Suppose A and B are the Boolean variables. The OR operation between these two operands we can write by using any one of this symbol. As a binary operator, in general, it may be on any number of operands. Whenever the operator is a binary operator, we prefer to look to the result of the binary operator on 2 variables and on 3 variables. While looking to the result of the binary operator on 2 variables and on 3 variables, it is possible in general to look what is the result of the operator on any number of variables. So, to look to the result, we will be listing here all possible values on 2 binary variables, and also we are listing here all possible values on 3 binary variables. So, if we list possible values on these 2 Boolean variables or binary variables, these are the possible combinations on these 2 binary variables. Similarly, if we look to the possible values on these 3 binary variables, these are the possible values on these 3 Boolean variables or binary variables. While having OR operation between these 2 operands, the result we'll be looking as, for first combination it is 0, for the remaining combinations we are looking to the result as 1. Similarly, on these 3 Boolean variables, the possible values, if at all we are looking to the result, except for the first row, for the remaining rows we are reading the result is 1, whereas for the first row we are looking to the result as 0. The result we prefer to read with one of the Boolean variable. Let us name the Boolean variable as y, so that while looking to these results, it is possible to define this OR operation as the result of OR operation is 0. The result of OR operation is 0 if and only all Boolean variables are with a value of 0. Or equivalently, we can talk the result of OR operation is 1 whenever at least one of the variable is 1. To perform all these logical operations, we are having hardware devices. These hardware devices we are naming as logic gates. These logic gates are basically implemented by using few basic electronic devices such as PN junction diodes, BJTs, MOSFETs, etc. But it is possible to learn this subject, this electronic subject, it is possible to learn without knowing inner details about the logic gates. I mean, without bothering to the inner circuitry part of the logic gates, it is possible to learn this subject. The device which is performing this OR operation, this device we are naming as OR gate. Symbolically, we are representing this OR gate with this symbol. It may be having, say, a number of inputs. The gate, if at all it is having n number of inputs, then we are naming the fan-in of the logic gate is equal to n. So that the word fan-in is basically referring to the number of inputs to a logic gate. Say for example, if at all we are having a OR gate, the fan-in is basically talking about the number of inputs to a logic gate. If at all OR gate is having 3 inputs, then the fan-in of that particular OR gate we are naming as 3. Or equivalently talking, if fan-in of a OR gate is say 5, default means it is giving the meaning as that particular OR gate is having 5 inputs. It is a means of the word fan-in. If we look to the next operator, we listed the next operator as we named as AND operator. This AND operator symbolically we are representing by using any one of this symbol. While taking A and B as Boolean variables, the AND operation between these two operands we can write by using any one of this symbol. Let us name the result as y. In general, the binary operator it may be on any number of operands. Generally, while writing AND operation, among these operands we may not be writing even this dot. Even without this dot also, default means we are taking as among these operands there is an AND operation. If you look to the result of this AND operation on 2 variables, we are looking to the result except to the last row. For the remaining rows the result is 0, whereas for the last row it is 1. Similarly, if we work for the result on 3 Boolean variables, we are looking to the last row result as 1, and for the remaining rows the result is 0. So based on this result, it is possible to speak verbally about this AND operation as the result of AND operation is 0 whenever at least one of the variable is 0. Or equivalently, we can talk the result of AND operation is 1 if and only all the variables are 1. To perform this AND operation, the logic device is AND gate. Symbolically, we are representing this AND gate with this symbol. We are looking here in these tables. For example, this is a table we developed on 2 Boolean variables. And while listing the possible combinations, we are looking, there are 4 possible combinations, hence we are looking to the 4 rows in this table. Similarly, it is a table we developed on 3 Boolean variables. While listing all possible combinations, we are looking, there are 8 combinations, so that the table we are looking 8 rows. We are looking in these tables the possible values of the Boolean variables along with the result. Such table or tables we are naming as truth table. So that the truth table is the one which is consisting of all possible combinations of the Boolean variables along with the result. And generally, whenever we are developing the truth table, say for example n Boolean variables, we prefer to list the binary combinations in such a way that they must be in the decimal increasing order. Even if at all we are looking here on these 3 Boolean variables, if we look to the equivalent decimal number for each one of these binary combination, we are looking as 0 to 7. So in general, if at all we are talking, whenever we are developing a truth table on n Boolean variables, we prefer to list the binary combinations in the decimal increasing order. The next operator we are looking as NOT operator. As I mentioned, it is a unary operator. Symbolically, this NOT operator we are writing by using any one of this symbol. While taking a as a Boolean variable, the NOT operation on this operand we can write by using any one of this symbol as like this. Because of only one Boolean variable, we are looking, there are 2 possible values on the Boolean variable, and we are reading here y is not equal to a. Whenever the binary variable a is the value of 0, not equal to 0 stands in the Boolean algebra or in the binary number system, it is 1. Not equal to 1, it is second case, so that it is giving the value as 0. To perform this NOT operation, the logic device we are having as NOT gate. It is a symbolic representation for NOT gate. It is also named as inverter. Why we are naming this device NOT gate as an inverter with a well meaning we can understand while looking to this truth table. Basically, we are looking, this device is interchanging the Boolean constant value. If input is 1, output is 0. If input is 0, output is 1. So basically, the values of the 0 and 1 are interchanged between the input and output is the reason to name the device as inverter. While dealing any mathematical subject, few of the standard relations what we need to use very frequently, such relations we used to name as properties. As similar to any other mathematical subject, here also on these operators we are having possibility to list few properties. These properties here we are naming as Boolean algebra properties. So we are listing these relations on these operators under the heading of Boolean algebra properties. If A is having OR operation itself any number of times, it is A. If A is having AND operation itself any number of times, it is A. If A is having OR operation with a Boolean constant 0, it is A. If A is having AND operation with a Boolean constant 1, it is A. If A is having OR operation with a Boolean constant 1, it is 1. If A is having AND operation with a Boolean constant 0, it is 0. If A is having AND operation with its complement, it is 0. If A is having OR operation with its complement, it is 1. In fact, what is the list we made here? All these are covered already while giving the truth table on two binary variables with OR operation as well as with AND operation. We can look here, the second property and third property, what we name, what we listed. These are basically, you can see from this list. Here we are looking, if at all one of the variable is 0. So one of the variable is 0. Suppose if we take A is 0, for this OR operation, we can look what is the result. And similarly, for this AND operation, whenever we are having a result, if you look to the first property, A or A, any number of times it is A. So while looking to this two variable truth table, you can see while looking at the first row and last row. In the first row, A, we are having the value as 0. So 0 or with 0, any number of times it is 0. For the last row, A is with the value of 1. So 1 or with 1, any number of times we can look as 1. So what is the value of A we are having, that we are looking as a value, as a result. And similarly, if we look to the OR operation for this case, so here, what are the list we made here? In this list, we are looking all these relations as pairs. And if you look, there is a specific relation within the pair. In this equation A, we are having this OR operation, while coming to B, it is changed to AND operation. Similarly, in this equation A, we are having AND operation, while coming to B, it is changed to OR operation. So basically, we are looking, there is interchanging of this OR AND operators. And also we are looking, there is interchanging of the Boolean constant 0 and 1. There is interchanging of the Boolean constant 0 and 1. Any pair of equation or expression is following this relation, such pair we are naming as dual pair, and this property we are naming as principle of duality. This property we are naming as principle of duality. It is one of the important property. Generally, we will be looking to the questions using this property. So in the principle of duality, what we are looking is, there is an interchanging of the Boolean constant 0 and 1. There is an interchanging of OR and AND operation. So in the principle of duality, basically what we are looking is, there is an interchanging of OR and AND operator, and there is an interchanging of Boolean constant 0 and 1. Can list the next property. The Boolean variable, if at all it is having complement twice, it is the variable A. We can prove this easily. Suppose if at all A is 0, while taking one complement it is 1, while taking one more complement it becomes 0. We started with 0, we are reaching to 0. If at all we are starting with 1, we will be reaching to 1. The next property we can list as A OR with BC is equal to A or B AND with A or with C. The name of this property is distributivity. what are the properties we listed till now until to this 4? We are having the proof for all these properties while looking to these truth tables. We can verify easily if at all we are having, say for example, a 2 input OR gate. The first 4 properties we want to see the proof. We can look easily the proofs from this truth table with the usage of the truth table. Suppose if at all we want to look the proof of this relation or this property, we are looking A or 1. Suppose B, if at all we are talking as a 1. So if at all we are having a B is 1, we are looking A may be 0 or A may be 1, we are having a result is 1. So that while having one of the variable is 1, we can talk the other variable may be of anything, the result is 1. Similarly, we want to see the proof for this relation. If at all we are looking to the B is 0, for example here to map with the truth table. So B is 0, we are looking B is 0, we are looking for this first row and this third row. So we are looking here A may be of any value, the result is 0. Like this, it is possible to verify the results what we mentioned here in this list with the help of these truth tables. In general, if at all we want to see the proof of any such Boolean equation, the proof of such Boolean equation is possible with the 2 procedures. One procedure is very similar procedure of the conventional algebra. In the conventional algebra, we may be looking to the proof of the equation. We may be starting with LHS expression. While doing some mathematical manipulation, we will try to read the result is to be RHS. Or sometimes we will be starting with RHS. While doing some mathematical manipulation, we will try to read the result is to be LHS. So the similar procedure we can use even in this Boolean algebra also to see the proof of any Boolean equation. A part of this procedure, we are having other alternative procedure to see the proof of the Boolean equation. We are basically developing the truth table for LHS expression as well as for RHS expression. While looking to the result of the LHS expression and RHS expression, if the results we are looking row wise same, then we are talking the relation is true. If at all we are looking at least any one of this, at least one of the row, the LHS and RHS result is not same, then we are talking the relation is not true. So it is the other alternative procedure to see the proof of any Boolean equation. Let us try to see the proof of this distributivity with this second procedure. This property we are looking, it is on 3 Boolean variables. While listing all possible values on these 3 Boolean variables, these are the possible combinations on these 3 Boolean variables. If we look to the result of LHS expression, we are having the LHS expression as A or with base C. If at all A is 1, B and C may be of anything, the result must be 1. Of course, this we are talking while looking to this third property. Based on this, we can see for the last 4 rows A is 1, so that the LHS result is 1. Similarly, if B and C is 1, A may be of anything, the result must be 1. To read B and C is to be 1, B as well as C both must be 1. So we are looking here for this row B and C is 1, so the result is 1. Even for this row B and C is 1, hence the result must be 1. Of course, this 1 we already mentioned because of this A. No need to write again because of B and C. No need to write because of B and C that we are talking while looking to the first property. While looking at the first property, it is possible to speak 1 or with 1 any number of times, it must be 1. So that no need to write again because of B and C. And of course, for other remaining 3 rows, the result must be 0. Similarly, if we look to the result of RHS expression, the RHS expression we are looking as A or B and with A or C. To read this result is to be 1. This A or B must be 1. This A or C also must be 1. So, equivalently it is possible to speak among these two terms, if at all we are looking any one of the term is 0, then the result must be 0. So, based on this, if at all we are looking here A or B is 0, so that it is 0. The same rule holds even here also, it is 0. Here A or B is 1, but A or C is 0, so that 0. Here A or B is 1, A or C also 1, so that the result must be 1, and so on. We can read the result as like this. So, we are looking here row wise result of LHS and RHS expression is same. Once the row wise the result of LHS and RHS expression is same, then we are talking the relation is true. If you write the dual for this, A and with B or C is equal to AB or with AC. But all we are giving the proof to the A, if at all B is the dual of A, then no need to see separate for B. What the proof we are having for A, default it is valid for B. The condition is B must be the dual of A. As long as the B is the dual of A, default the proof of A is valid even for B. And we can list few more properties. A or with A complement B as A or with B. We can prove this easily by using this distributivity and few other earlier properties. We can look here A or with A complement and with A or B. A or with A complement using fourth property we know 1. So, 1 and with A or B. So, 1 and with anything is anything is A or B. Similarly, A and with A complement or B is equal to AB. A complement or with AB is equal to A complement or B. Again, the proof of this also we can look by using this distributivity and few other earlier properties. The dual is A complement and with A or B is equal to A complement B. A or with AB is equal to A. So, to prove this, we are not using distributivity. Basically, we are looking A as a common, so that 1 or B within the parenthesis, 1 or with anything using this third property we know it is 1. So, 1 and with anything using this second property we know it is A. The dual for this A and with A or B is equal to A. AB or with A complement C or with BC is equal to AB or with A complement C. The name of this property is consensus property. It is also one of the important property. The importance of this property we can look by looking to this equation itself. The purpose of all this mathematical work is basically to reduce the cost of the logic circuit. Suppose we want to realize this LHS expression, then because of 3 terms we are in need of 3 AND gates, and of course we need a OR gate. We're taking OR operation among these three terms. Whereas for RHS, if at all we are looking, we need only two AND gates and one OR gate. So straightforward, we are looking with the RHS expression, the number of logic gates are less comparing with the LHS expression. Not only this, the OR gate what we are using to realize RHS expression will cost less comparing to the OR gate what we need for realizing LHS expression. The reason we can understand as this OR gate is having the fan in as only 2, whereas this OR gate is having a fan in as 3. Hence, whenever we are estimating the cost of the logic circuit, apart of looking to the number of logic gates, other equal important parameter what we need to look is the fan in of a OR gate. If the fan in of OR gate is less, the cost of the logic gate will be less. Hence, the fan in also one parameter to estimate the cost of the logic circuit. So, based on this, what I said is coming to be true. It is also one of the important property. We are going to use this property very frequently when we are doing the simplification of the Boolean functions or equations using properties. It is possible based on this property, if at all we are looking three terms with this relation, possible to replace these three terms with only two terms. And if you look to the dual of this property, A or B and with A complement or C and with B or C is equal to A or B and with A complement or C. The next property as X or Y and with X complement or Z, it is equal to X Z or with X bar Y. We can prove this relation using consensus property and few other earlier properties. If at all we are expanding LHS expression, we know X complement or with XZ or with YZ or with X bar Y. We know using fourth property X complement is 0, and among these three terms we are having possibility to use this consensus property. So we can see using this consensus property what relation we are looking among these three terms. If you name it is a reference term, first term if at all we are taking as a reference term, we need a second term in which one of the literal of the first must be complemented. This happens so in this second term we are having complement of one of the literal of the first term, and if at all we are having a third term which is coming from the first two terms second literals, we are having a third term which is coming from the first two terms second literals, we are having possibility to eliminate this third term. It is a thing what we are having with this consensus property, so that any expression which is having three terms, on such expression it is not possible for us to use the consensus property. To use the consensus property among these three terms, we need to have such a relation. Say for example, if at all we are having a expression with these three terms, on this expression it may be having three terms, but it is not possible for us to use the consensus property. To use the consensus property among these three terms, we need to have such a specific relation. But all we are looking here, if you name it is a reference term, it is possible to accept it is a second term. The reason is one of the literal of the first term is complemented here, and we are having a third term. We are looking it is coming from the first two terms second literals, so that we are having possibility to eliminate this third term. Hence, we are looking to the relation, the result as XZ or with X complement Y. The dual for this is XY or with X complement Z is equal to X or Z and with X complement or Y. The next property we can list as A or B or C and so on whole complement is equal to A complement, B complement, C complement and so on. the dual we can read A, B, C and so on whole complement is equal to A complement or B complement or C complement and so on. The name of this property is De Morgan's property. So in this De Morgan's property, also we are looking interchanging of OR and operation, which is similar to the dual property. And also we are looking if at all B is having the complement, while writing the De Morgan's property, the result we are looking B without complement. So that we are looking literal is complemented. Based on this, it is possible to speak we are having interchanging of 0 and 1. So that these are the three changes what we are looking in the De Morgan's property. Whereas the dual property we are looking only these two changes. So it is the difference what we are looking between the dual and the De Morgan's property. Here I use the word literal. The meaning of the word variable and literal. Truly speaking, the word variable is referring to only uncomplimentary form of the variable. Variables are available only in uncomplimentary form. The complementary form of the variable we are reading while using a not operation. Whereas the word literal is referring either may be uncomplimentary or complementary form of the variable. So by using this terminology, if at all we are looking at the difference between the dual operation and the De Morgan's property, dual operation and the De Morgan's property. In the dual operation, the literals are not going to affect, whereas in the De Morgan's property, every literal is going to be complement. It is the difference what we are going to look between the dual and the De Morgan's property. Based on this, let us look a small example. Suppose we want to read the dual result and De Morgan's result of this Boolean expression. The dual result of this Boolean expression we are going to look as E and with F complement. As we said, literals are not affecting the real operation. So that E without complement, F is with a complement. So E and F complement are not affected, but as we know, R and must be interchanged. This R becomes AND operation. Later, this AND becomes R operation. This R becomes AND operation. This AND becomes OR operation. Finally, this OR becomes AND operation. So it is the dual result of this Boolean expression. And we are looking here, whenever we are having a given Boolean expression, many parentheses, many brackets like this, we need to apply the dual operation from innermost parenthesis. So while looking to the real operation from innermost parenthesis, it is the result what we are having is the real result of this given Boolean expression. As similar to this, if you look to the result of, as similar to this, if you look to the result of the De Morgan's property, it is coming to be E complement and F. We are looking E without complement, so that in the De Morgan's property, as we said, every literal is to be complemented, so that E is coming with a complement, F is with a complement, so F we are looking without complement. R becomes AND. Then this AND becomes OR, D without complement, and so on. We can look like this. So it is a De Morgan's result of the given Boolean expression. So while looking to the dual and the De Morgan's result, it is possible to speak If you know the dual result of the given Boolean expression, from this we can read the De Morgan's result simply taking complement of every literal. So while taking the complement of every literal, it becomes the De Morgan's result of the given Boolean expression or vice versa. So as we said, these are the few important relations what we are looking on these basic operators, and, or, and not. Suppose if you write the function f of x, y, z, as long as x, y and z are the Boolean variables, the function f we are naming as the Boolean function or switching function. Suppose we are having the Boolean function f as x, y complement or with y, z or with x complement z. This form of expression we are naming as sum of product expression. Here the word sum is referring to OR operation. The word product is referring to AND operation. Similarly, if you write other function, say while naming earlier function as f1, let us name this is f2, f2 of ABC. As long as a, b and c are the Boolean variables, the function f2 also we are naming as the Boolean function or switching function. Consider this Boolean function or switching function is having as a or with b complement or c complement, and with a complements or c and with b or c. This form of expression we are naming as product of sum expression. Whenever we are having an expression in the SOP form, or whenever we are having expression in the POS form, how to develop a truth table maybe for a SOP expression or maybe for a POS expression we already covered while giving the proof of distributivity. If you look to the distributivity property proof, we were looking earlier what we covered. LHS expression was A or with BC, it was SOP expression, and RHS expression was A or B and with A or C. So it is a POS expression. For this SOP expression and the POS expression, we already developed the truth table. Hence, we know the procedures how to develop the truth table, maybe for a SOP expression, maybe for a POS expression. Now let us take the problem in reverse. Suppose consider we are having a function f which is defined in the truth table as like this. Now let us try to see how to write the SOP expression as well as the POS expression for this function f which is defined in the truth table. Let us try first for SOP expression. To write the SOP expression of the given function when it is a truth table, we are referring to only those combinations of the truth table where we are having the function output is 1. While referring to these combinations, for each one of these combinations we are going to write the product term. To write the product term for each one of these combinations, the rule what we are following is, in general, if at all the variable x, Boolean variable x is the value of 1, it is present in the product term without complement. Or if at all the variable x is the value of 0, it is present in the product term with a complement. So based on this rule, if at all we are looking here, we are having here A0, B0, so that in the product term of this combination A and B we are looking with a complement. Whereas the value of the C variable is 1, so C will be in uncomplementary form. Similar to this, if you come to the next row, we are looking A complement, B, C complement, because A and C are the values of 0, hence we are having complement on these A and C variables. b with the value of 1, it is uncomplementary form, and so on. If you write like this, it is a b complement c complement, here it is a b c complement. Now we are taking OR operation among all these terms. While writing OR operation among all these terms, we are looking here, it is a complement b complement c, or with a complement b c complement, or with a b complement c complement, or with a b c complement. This form of expression very similar to the equation x what we mentioned earlier, so that we are naming it is sum of product expression. Till now we are discussing some properties. Using properties, it is possible to do some simplification on this equation. It is possible to group this second term with the last term. While grouping the second term with the last term, we are looking the product term as BC complement, so that we are eliminating the variable A. So basically what we are looking is, among these two terms, BC complement is common. Within the parenthesis we are looking A or with A complement, it is a fourth property what we learned, it is 1, and we learned 1 and with BC complement, 1 and with anything is anything is BC complement. As similar to this, it is possible to group the last two terms also. While grouping the last two terms, the term we are looking as AC complement. And of course, first term not possible to group with any other term, so that we are keeping as it is. This equation 2 also very similar to the equation x, hence we must name this equation also as sum of product form. There should not be any confusion about the usage of this last term to group the second term as well as the third term. It is possible to group the last term to group with the second term as well as third term based on the property what we learned as the first property. Based on the first property, we know A or with A any number of times it is A. Another way, if at all A is appearing once, we can use it as many times as we need. So for example, if at all possible to group the first term with the, if it is possible to group this first term with the last term, even further also it is allowed to use. Of course, it is not possible, so we are not using. Otherwise, if it is possible, we can use. But of course, we know well the same thing is not true in the conventional algebra. In the conventional algebra, if at all we are grouping one term with any other term, the term we are not going to group with any other term. In this Boolean algebra, of course, here it is possible. The reason we can understand the number system what we are having here is the binary number system. It is the reason why it is possible. And we are looking here, the equation 1 and equation 2 both are SOP expressions, but there is a clear difference between the equation 1 and equation 2. In the equation 1, we are looking all the terms with all the variables, whereas in the equation 2 we are not looking all the terms with all the variables. Based on this difference, we are naming the equation 1 as canonical sum of product expression. So that in the canonical sum of product expression, we must read all the product terms with all the variables of the given function. In other way, whenever we are having the expression every term with all the variables of the given function, then only we are naming that expression as the canonical sum of product expression. Hence, the equation 2, it is not possible to name as canonical SOP expression. And also, each one of the term in the canonical SOP expression, we are naming as min term. So if you want to define the word min term is a product term in which all the variables of the given function must present, and for that combination the function output must be 1. For that combination the function output must be 1. So that we should not define min term as it is the product term which contains all the variables, but all we are stopping the statement with this, it is incomplete. We need to add further as min term is a product term which contains all the variables of the given function. For that combination the function output must be 1. These minterms we are representing with a small letter m. Again, to distinguish various minterms of the given function, we are using here a decimal subscript. Here it is m1, here it is m2. The decimal subscript meaning we can understand easily. For this binary combination, the decimal equivalent value is 1, so that we are using here the decimal subscript is 1. For this binary combination, the equivalent decimal value is 2, so that we are using here the decimal subscript is 2, and so on. Here it must be 4, here it must be 6. So by using this terminology also, we can write the SOP expression as m1 or with m2 or with m4 or with m6, or equivalently we can talk sigma m 1, 2, 4 and 6. These equations also we are naming as canonical SOP expression. Again, to distinguish between 1 and 1 dash, 1 dash we are naming as compact canonical sum of product expression, whereas equation 1 we are naming as expanded canonical sum of product expression. So it is a procedure to write the sum of product expression of the given function whenever the function is defined in the truth table. As similar to this, let us work, if at all the function is given in the truth table, to write the POS expression, the procedure what we are following is, here we are referring to the combinations of the truth table where the function output is 0. While looking to these combinations, we need to write sum terms. To write the sum terms, the procedure what we need to follow is, if at all the variable is having the value as 0, it is present in the sum term without complement. If at all the variable is having the value as 1, it must present in the sum term with a complement. By using this rule, if you write here a, b and c all are with the value of 0, hence the sum term we are looking a or b or c. Coming to this combination, a is 0, b and c are with the value of 1, so that b and c were reading with a complement, and so on. Here it is a complement or b or c complement. Here it is a complement, b complement or c complement. After writing sum terms, among these sum terms we need to take AND operation. We need to write AND operation. F of a, b, c is equal to a or b or c and with a or b complement or c complement and with a complement or b or c complement and with a complement or b complement or c complement. This equation 3 very similar to the equation y, hence we must name this as product of sum expression. On this equation 3 also we are having possibility to apply few earlier whatever the properties we learned, the Boolean algebra properties we can use, and we can see simplification on this equation 3. It is possible to group this second term with the last term. While grouping the second term with the last term, we can read the sum term as b complement or c complement. So we are basically eliminating the variable a. So we are using here basically the distributivity property. It is a second term what we are looking. It is a last term what we are having. Suppose b or b complement or c complement if you name as x, we are looking here it is a or x, and with a complement or x, using distributivity we are looking here it is nothing but x or with a complement. So as you know, a complement is 0, 0 or with anything is anything, hence it is x. X is nothing but b complement or c complement. Similarly, we can group this third and fourth term which is giving a complement or c complement, and the first term not possible to group with any other term, we are keeping as it is. And we are looking here this equation 4 also similar to the equation y, so that we must name even this equation also as a product of some expression. As similar to the SOP, we are looking there is a difference between the equation 3 and equation 4. In the equation 3, we are looking every sum term with all the variables of the given function. Whereas in the equation 4, we are not reading all the sum terms with all the variables. To distinguish these two POS expressions, we are naming the equation 3 as canonical product of some expression. So that in the canonical product of some expression, we need to read all the sum terms with all the variables of the given function. Of course, variable may be complementary or in complementary form, it is a different issue, but all the variables of the given function must present. Then only we are naming that expression as canonical POS expression. And each one of the term of canonical POS expression we are naming as max term. We are representing with the capital M, so that we can define the max term as max term is some term which contains all the variables of the given function. For that combination, the function output must be 0. The max term is some term which contains all the variables of the given function, may be variable complementary or uncomplementary form. And for that combination, the function output must be 0. Here also we are using a decimal subscript to distinguish various max terms of the given function. By using this terminology, we can read the expression as M0 and with M3 and with M5 and with M7, or we can read alternatively pi m of 0, 3, 5 and 7. This equation let us name as 3 dash. It is also we are naming as canonical POS expression. As similar to SOP case, 3 must be named as expanded canonical POS expression, whereas 3 dash we must name as compact canonical product of some expression. So it is a procedure to write the product of some expression of the given function as and when the function is defined in the truth table. So in general, the procedures what we said for writing SOP and POS expressions, these procedures are valid for a function. Function may be on any number of variables, maybe on 3 variables or 2 variables or 4 variables or 5 variables. Function may be on any number of variables. It is a procedure we need to follow to write the sum of product expression and to write the product of some expression.